real estate pricing prediction is a fascinating problem, and it is as fascinating as predicting stock market pricing, etc., because there are so many variables that can affect the pricing of a real estate. So in this video, we are going to look at a synthetic data to predict real estates, and we're going to look at a couple of algorithms, and one of them being simple linear regression like this. So to give you a very, very brief high-level overview of what and how linear regression works. So imagine these are all data points over here, and imagine these are like the housing sale data, and maybe this is the size of the house, right? So you would get to plot all these things on X and Y axis, and to predict any new house that you don't know the price of, let's say that you know the size of that house, maybe that is somewhere over here, and then you should be able to plot this out, and you should be able to plot the pricing. So essentially, if you just have this line over here and imagine all the pricing that would fall, it's all on here on this axis, and then all the pricing would be up here. So if you had a very big house with a lot of space, maybe that's up here on this line. Of course, there might be some difference in terms of the amount of error it has, but nonetheless, it is close enough to what we would expect. So this is how linear regression works. We are just plotting a straight line through these data points and then try to minimize it based on the errors that we are able to see between the actual price and the predicted price, and then build a line out. So that's a quick overview of it, but let's jump into the actual code and let's run through this, and hopefully this should give you a bit more insight into how linear regression works, and then we'll also look at gradient boosting as well. So as always, let's bring in these two handy libraries, pandas and numpy, and let's also create some synthetic data. Again, if you've seen my previous videos where we are just creating synthetic data, you don't have to worry too much about how we are doing this. It's only synthetic data, but in real world, you probably have access to some real data. But in this case, we just want to get something out where we can understand all these algorithms. So we have all these variables, and let's put them all into a data frame. So size is coming from here, and then location is going there, and price is over here, and this would create a data frame for us. So let us visualize the data by first looking at a table view of this. So we have the size and the location. Presumably these are like different locations in a city, so they'll obviously have different pricing, and the size of the house might be one other thing that might have an effect on pricing, and this is the final sale price that we have over here. So if you think about it, we have like two features which we want to use to predict our pricing of the real estate. So this is a good hypothetical synthetic data that we have. So let's keep progressing and look at linear regression first. So I'm going to bring all these packages in. Mostly these are all scikit-learn packages. And again, I've got this pip install over here, which you can use to run and set up your environment so that all these packages are available. And then the first step we want to do is look at the data. And then let me show you what this does. If I run this line, so see that we have the data in this shape over here, size and location. Now, if I just run this line, you'll see that we have pivoted it around the location now, so that we have the size, price, and the locations are all on their own column. So we have location 10 here, location 2 here, 3 here, and so on. So it's encoded our data so that instead of having one location column, we have multiple location columns, and all these are going to be features that are fed into our model to predict the price. And we'll also create our X variable where we are just dropping the price. So the price is actually Y variable, so we'll put that into Y variable. So now we have Y variable which has just the pricing in it, and we want to again do our train test split, right? Because that's what we've been doing so far, and this really helps in validating our model. And in real world, you probably also have an evaluation data set, which is something completely different from what you have in training, and then you can use that to predict the accuracy. But in this case, we are setting 70% into our training set, and the test set will get 0.3 or 30%, and we get like these four variables, which is X train, Y train, X test, and Y test. So we'll initialize our model as well, as simple as this, because sklearn made it so straightforward for us. And then model.fit on X train and Y train, that is the 70% of data. So we've got the model.fit now, so we can do the predictions. So let me just run this. And to predictions, we are setting the X test, which the model hasn't seen. So remember, the model has only seen the training data set, but we can predict the test data set so that we are able to calculate the accuracy. And once we do this, we put that in the predictions variable, which is coming here. And the y-test is coming from here, which is the real world data. So y-test is the actual data, and this is the predicted data for the same real estate data set, right? Because if you want to compare how well our model predicted these things, so I'm just going to run this and print this out. So you'll see the real estate price prediction mean squared error is this much. Again, there are other steps as well, like cleaning the data, normalizing the data so that we don't have such a huge number over here. So you would normally normalize that y variable to be somewhat very similar to like between 0 to 1 or 1 to 100, whatever it is. But yeah, in real world, you wouldn't have all these numbers as it is in hundreds or thousands of dollars or in millions. But nonetheless, this is good enough for us to get just a good introduction into linear regression. Let's also plot the feature importance, right? So we want to know, out of all these location data that we saw, which locations contributed to most to the pricing that we've seen. So that's the question, because maybe your stakeholders or yourself want answer for this to understand what locations are contributing the most prices. So we can run this matplotlib, bring that in, and then here we are just bringing in model.coefficients, which is the feature importance, and the features are going to be the X columns. So we can check out the features. So these are all our features, and feature importance is just another array of numbers here. But it's much better to visualize this rather than look at these numbers. So let's plot a bar chart of these two, and let's do some labeling, add some ticks, and actually let me just change this to 15, and let me do plot.show. So this is what we get over here, and you'll see that these are all the locations that we have, and this is the size which is contributing the most, the least actually, and location 6 looks like is contributing the most negatively, and on the positive end we have like location 9 over here, and maybe this is location 3 if I'm right. So yeah, this is what we would need. Actually, let me just change that back to 45 and run this again. And you'll see location 2 is I guess contributing more. So if you have a real estate in these two locations, that means the price is going to be really high compared to some of these locations which are over there. So this is good. Now let's also run some predictions, because that's what we are here for. So imagine you had another house where the size of that was like 2,000 square feet. Let's do that. And then maybe this house was in location number 5. And we want to predict how much this price is going to be for this location and for this size, right? So I've created a function over here which takes in a size and location, and let's check that function out. So here is that function where we have the data frame, and we just pick out that input data, and we again transform all that data to pivot it out. So similar to what we did just here, get dummies does that, and then we call the model.predict on just that input data, and that should give us the prediction. So let me just run all of this first. So that's initialized, and I can come in here and run predicted price on it. And right now we have the predicted price, which is this, but we can print this out in that fancy print statement so that it's much more readable. So the predicted price for the property of size 2,000 square feet in location 5 is this much, 595,ish dollars. So that's good, but we can keep moving on and see how we can improve on this model. So one of the things that I would like to do is also plot the predictions against what the real world data was, so that it gives me an understanding of how good the predictions are at different intervals, right? So let me just bring this matplotlib library in. And then here we have a fancy function where, again, we are doing very similar things. We take all the sizes, we take all the locations that we get, and then we just loop through them in the size and location combination, and we do the model.predict and put all of that into a predictions array over here. So this is if you're passing in a list of locations and sizes. If it's not a list, imagine if it were just a single location, then you would just run this section over here in the else statement. So this is okay for now. Let me just run all of this, and let's come down here. So here we want to generate some synthetic data for plotting, and we'll do that by running linspace on this. So if I just run this and look at the sizes that we have, we see we have some random sizes between 500 and 4,000 of 100 counts. And the location, we'll do the same as well. And if you check out the location, they're all location 5s. So we've got 100 locations for 100 different sizes, and we can run a predict function on all these. So if you remember, predict price, which we initialize here, it takes in the list as well as non-list. So we are giving it a list of 100 size and 100 location. We can do that now. And we are just going to plot all of this now. Let's plot a scatter plot on this. So this is the actual data that we're getting. So you remember, this is data size and data price, which is all coming from up here, which is the data that we already had. And all we're doing here in this linspace is trying to predict the line, right? So we want 100 dots so that we're able to build a line. So this is all the predictions, and we want to put all that in here, predicted price. So let me just run that. And all this will make sense in a second. And I'll just run through these four, which are like the same across all the other plots that we've seen so far. We just give it a label, the title, a legend, and then do plot.show. And if I do this now, you will see we have this red line, which is coming from all this, a linspace where we initialized 100 points and 100 locations and did the prediction. That is where this line, red line, is coming from. And all these blue dots, which is the actual data over here, these are all coming from the actual data that we had over here in this data frame. So we are able to see that if our house was somewhere over here, then we would be predicting a price here, although it can be down here or here as well. So this is good. So this kind of gives an indication of how the price is averaged out when we build this linear model. So this is good. Now, we don't want to stop there because we want to try out different algorithms, because that's what we are here for, right? So next one is we are doing some gradient boosting. So gradient boosting is an ensemble technique. And again, there are various videos that I've made on random forest, ensemble techniques and other things. But to just give you an understanding of this, so imagine this is the error term, and these are the number of iterations that we're going through. And we start off with just one tree where we build a simple tree, and then we make a prediction, and all the wrong values get high probability of again appearing in this section over here of this tree, and we take and build more trees on this, and then we keep progressing so that the error term keeps reducing and reducing. Another way of looking at that is like this. So we start off with a random subset of data over here, we train it and build a random forest like this, decision tree. And then we take some of the red dots over here, which are like all the wrong predictions, and some other correct predictions as well, and then train it again to understand this data better. And out of this, we'll probably predict these two correctly, and then these two are wrong still. So those appear in this tree again, and then we train and test, and then finally we have all these blue, which are all the correct predictions, and then we have an ensemble prediction over here. So this is how gradient boosting works. Of course, there are XGBoost and other things which are like computationally much better, parallelized and other things, but for now, gradient boosting is all we wanted to understand. So using this is very straightforward. There is scikit-learn has made it really easy to import this. So let's import this as well. Initializing it is straightforward, and we'll do the same on model train and the test data, because we already have defined this. So if you see here, I already have train and test, which is coming from up here when we did the linear regression. So I'll just do a model.fit on this. Prediction, MSC, printing, they're all the same, I guess, over here. But what is important is, let's see what feature importance the gradient boosting algorithm gave to our features, right? Because if we saw here, so this was what we got with linear regression, where some of these locations had higher or lower kind of weightage in terms of predicting the price, whereas size did not have much. Now, let's see what this gives us now. So again, the code is very similar to the above, but I'll just run all this just at once. So if I run all of this at once, you will see in this gradient boosting technique, size has a lot more weightage in predicting the pricing rather than all these locations. Although some of them have some weightage, but not as much as what we would see in this. So right there, we see that these algorithms perform very, very differently. And let's also do some predictions as well. So we'll give the same location and the square feet that we had and predict the price, and let's do this. So even here we are getting something similar. So I believe if it was like 59 we got with linear and this 56, they're close enough. But what I'm also interested in is looking at plotting these predictions. So remember, against what we had here, where we had all these points and we just got a straight line through for linear regression, I'm interested in understanding how well the gradient boosting method was able to pick all this out and see if it's any different. So it's same what we did above, where we have a linspace where we define random number of 100 points going from 500 to 4,000 and locations, do the predictions. And let me just plot all this because we're doing the same thing as above, where we are having the actual data, which is coming from size and price from here, from the data set that we initialized above. And then this prediction price is coming from all over here, which are just random variables. So let me just run this. Right, so if I run this now, you see this line, instead of being straight, it's all squiggly and it's non-linear, which is quite interesting because it's not just a straightforward model like this straight line. It's a bit more capturing a bit more of the nuances within the data. So hopefully this makes sense. So this was gradient boosting and some visualization that you can use to understand how good the model is. Again, you'd probably record all these things into a notebook or a monitor somewhere to keep an eye on how this is accurate, how well the MSE or mean squared error and other things are for different models that you want to try. Maybe further down, you can try gradient boostings, cousin, XGBoost, or random forest, or other algorithms that you want to try to predict the housing prices. Again, like always, I recommend you to go and check out some data sets on Kaggle website to practice some of this yourself on real world data as well. So until tomorrow, let me say goodbye and see you tomorrow.